Assalamu alaikum wa rahmatullah. Good day, students, and I welcome you all to the second class on PHY 1107 Practical Manual. Today we will begin with section 1.1 Significance of a Physics Practical. Physics practicals serve several essential purposes. The first one they mentioned in the book is verification of theoretical concepts. Practical experiments provide empirical evidence that validates theoretical predictions. Now, clearly, the first question that will come to mind is, what is the meaning of empirical evidence? What do we mean by empirical evidence? Well, scientists primarily rely on empirical evidence. Let me take a few minutes to explain that. Okay, empirical evidence refers to information or data that is obtained through observation, experimentation, or measurement. And all these three components are done in a physics laboratory. If you go to physics laboratory, you will make observation, experimentation, and measurement. These three, all of them. Okay? So empirical evidence is based on this. It is grounded in real-world experiences and is used to support or refute hypotheses, theories, or claims. Okay, so empirical evidence is a cornerstone of the scientific method and is essential for making objective and reliable conclusions. Empirical evidence has some characteristics that you should know. Let me mention a few of them. The first one is empirical evidence is observable and measurable. Observable and measurable, meaning you can observe it, you can also measure it. So empirical evidence is based on phenomena that can be observed, measured, and recorded. For example, the temperature of a body is observable, is measurable, and you can also record it. You can go to the lab, take an object, use a thermometer, measure the temperature. You see, it's measurable. You can also observe it. You can also record the measurement. The speed of an object is also observable. The mass of an object is observable, measurable, and can be recorded. All the physical quantities we are learning in physics are measurable and observable. So the evidence we give, if we say, for example, the length of a simple pendulum is 40 centimeters. This is an empirical evidence because you can go to the lab, take the string, use a meter rule to measure it. So that makes it observable and measurable. So with this, we can conclude that it is an empirical evidence. Empirical evidence is independent of personal belief, opinions, or biases, because the data is collected systematically and can be verified by others. Another characteristic of an empirical evidence is that it is reproducible. Empirical evidence should be replicable under the same conditions. If an experiment is repeated, the result should be consistent. If I do it 1,000 times, my result should be the same. If someone does it elsewhere, he should get the result I obtained here. That makes it reproducible. Empirical evidence, again, can be quantitative or qualitative. Quantitative means it can be given in form of numbers like 20 kilograms, 40 grams, 10 centimeters, or it can be qualitative based on description. That is, when observations are based on behavior or patterns, description, that makes it qualitative. In physics practical, we normally rely on quantitative empirical evidence because we are taking measurement in numbers. We record everything. We have table of values. We use them to plot graph. They are all numbers. That makes it quantitative rather than qualitative. By verification of theoretical concept, we mean physics experiment allows students to test and observe whether the predictions made by theoretical models hold true or not. For example, in the theory class, you were taught that according to Hooke's law, the force is directly proportional to the extension. The load attached to a string, for example, produces extension in the string. Now, the more load you attach, the more extension will be produced. You can go to the lab and verify this. You can go to the lab, conduct experiment to see if this is true or otherwise. Again, in electricity, we have Ohm's law that says the magnitude of current flowing through a conductor is directly proportional to the potential difference across the conductor. The formula says V equals IR. Now, you can go to a physics laboratory, conduct experiment to verify this, to find out if this is true or not. This empirical validation reinforces the credibility of scientific theories and ensures that they are not just abstract ideas but are grounded in observable reality. You will now believe that what scientists are saying is based on reality and not mere abstract ideas that cannot be verified. By observing phenomena directly, students gain confidence in the principles they have learned in class. This means when students conduct experiments and see the results align with the theoretical predictions, it strengthens their understanding and confidence in the principle they have learned in class, and making them more likely to apply these principles effectively in future studies or real-world scenarios. The second one is skill development. Physics practicals enhance critical skills such as observation, measurement, data analysis, and problem solving. As a scientist, physics practicals train you as a student to observe phenomena carefully, notice patterns, and identify anomalies. This involves paying attention to details and understanding the behavior of physical systems. Strong observation skills are crucial in fields like research, engineering, medicine, and even creative industries. For example, a medical professional must observe a patient's symptoms, while an engineer must notice flaws in a design. So many fields, observation is a skill that is required. Measurement, of course, measurement is a skill as a scientist. Physics practicals require precise measurement of quantities like length, time, mass, temperature, and electric current. Students learn to use instruments like rulers, calipers, stopwatches, thermometers, multimeters. Accurate measurement is fundamental in engineering, construction, manufacturing, and laboratory science. For instance, civil engineers must measure materials precisely to ensure the stability of structures. The next one is data analysis. Physics practical again involve collecting, analyzing, and interpreting data. Students learn to use statistical tools, graphs, and mathematical models to analyze experimental results and draw conclusions. Then we have problem-solving skill. Physics practicals often involve identifying problems, formulating hypotheses, designing experiments, and troubleshooting issues. Students learn to think logically and creatively to solve complex problems. These skills are transferable to various scientific and engineering fields. This means that the skills developed through physics practicals are not confined to physics alone. They form the foundation for success in various fields. Physics practicals are more than just experiments. They are training ground for developing skills that are essential for both scientific and non-scientific careers. Then we have understanding experimental uncertainties. Experiments sometimes reveal discrepancies between theoretical predictions and observed results. The theory will predict something, and then when you go to the lab, you will find otherwise. For example, classical mechanics fails to explain phenomena at the quantum level, which can be demonstrated through experiment. A few examples include black body radiation, photoelectric effect, Reed's combination principle, stability of atomic structure, Frank Haas experiment, Stan-Gallac experiment, Compton-Scattering, de Broglie hypothesis, Davison gamma experiment, and many more. Recognizing these limitations encourages students to think critically and explore more advanced theories or alternatives to explain them. In the next video, we will speak about conducting a physics practical. How do you conduct a physics practical? Inshallah. Assalamu alaikum wa rahmatullah.